An important note. It says in the syllabus, if you're not here, you're going to submit your homework in another fashion. It says, scan your pages and email them. I realized I forgot to upload this handout, but it does say in here, homework must be turned in early, prearranged absences. If you're not going to be here, email it to me in advance. Ideally, before the end of class. Homework which is submitted after the period in which the homework is due ends is at half credit. Some of you who send me stuff late will notice it says late across the top of your homework and then it's scratched out. This is your one freebie, people. If at 10:02 I walk out of the room and you catch me and hand me stuff, that's late. Please get me your homework on time. And if you're scanning, please send those scans at a high enough resolution that I can print them. I have bad eyes, why I wear these things. I will print them and grade them on paper and hand them back to you on paper. You think my handwriting's bad up here, you should see it on the iPad. So I try and stick to grading on paper as much as possible. If you have questions about the homework grades, please come talk to me. You can't read one of my comments, please come talk to me, we'll figure it out. Meanwhile, I want to go back to our idea of derivatives. When we created our derivative, we had this limit definition. But this was the derivative at a specific point. At the point A. But A doesn't necessarily have a value already established. So why am I using a different letter? Why not just leave it in X? If that's what I choose to do, then what I've created is a new function. And it assigns the value of the slope of the tangent line of f of x to every x value. It is a brand new function, which means it gets its own graph separate from f. Here's a graph I just made up. I'm going to pick a bunch of x values here. Yes. Yep, just a second. Down. Okay. Of course. So across the bottom, A, B, C, D, E, F, G, H, I, across the x-axis. Even if I know nothing about the equation that generated f of x, you can tell me about the sine of the slope of the tangent line. At A, if I were to draw a point at f of A, up there where I did, there's a tangent line there. What's negative? That point is positive. We're above the x-axis. Aha. If I were to draw a little bitty part of the tangent line up here, I would say, hey, that little bitty piece of tangent line should go like this. That's got a negative slope. That means at A, f prime of A is negative. What about at C? Looks like it should be a positive. At E, at F. Oh, now we're getting a little question mark. This negative and this negative. Because this is still a negative. F prime of F is negative. But look at the difference. This is a fairly steep line, yes? This is less steep. So it's less negative, but it is still negative. Just like if we compare the slope at H with the slope at I, slope at H is positive, but it's less positive than the slope at I. Here's another x-axis labeled with those same points, A through I. Let's guess at the values. At C, that's a positive number. But here's a question for you. Without caring about the direction, which is steeper? The tangent line over at A or the tangent line at C? Which one is steeper? A is going down faster than C is going up. Well, that means that the value at A should be more negative than the value at C is positive. Because that slope at A will be a more negative number than the positive number I get out of C. How does E compare to A? The slope here versus the slope here. Pretty damn close, aren't they? Fine. That means we'd make the points pretty damn close. I think E is just barely more negative. So I'll draw it a little steeper, but you don't have to. But how does E compare with F? Up there. The slope here versus the slope here. This is not as steep, so it should be less negative. Here, compared to here. Which of those is steeper? If H is steeper, then its slope should be bigger than the slope at C. What about here at I? Steeper still. I did skip a bunch of points. I skipped B and D and G. What's going on at B? I'm sorry, say again? The slope looks like it should be really close to 0. And at D, I think the same thing. And at G, I think the same thing. So if those slopes are actually 0, I play connect the dots. And this graph is the graph of my derivative function. Even without a single formula to my name. Given any picture, I should be able to create from it a picture of the corresponding derivative without doing any work at all. Page 154, that is an example in the text very similar to this. Questions? Yes, ma'am. I was eyeballing it. I guessed. Really, if I had a better graph on graph paper, I could have drawn the line bigger and counted boxes, right? I could measure the rise and measure the run and say, oh, that slope is this number. And then I could plot this more accurately. But I didn't have any of that advantage. So I just kind of said, all right, I'm going to make up a number for this. I know it's a negative something. And this is more negative, so it'll be a little bit lower. This is less positive than that is negative. So it's up, but it's not as far up as that one is down. This is where artistic merit comes into the game. And I am not an art teacher. But the idea is for me to simply say, is this a lot positive or a little positive? Is it more or less positive than something I was just looking at? If I had a table of values, I could approximate the value of my derivative. You did that already. In the homework, in the very first section, here is our step count. How many steps per minute at 20 minutes? Well, you take 10 to 20, you take 20 to 30, you figure out those average changes, and you use it to approximate the instantaneous change. But I'd rather get values. If I had a better picture, I would try and get better values off of it with measurements. And by the way, that is actually done in practice in several different pieces of software. They will simply take the graph and eyeball it, plot between values. Several different pieces of software. Hey, wait a second. I have a computer right here. Let's pick an equation. I'm going to graph this on the standard window, zoom option 6. 2x minus x cubed. Okay. Let's play this same game. If I were to draw the picture, what would I expect to see starting all the way over there on the left? If I drew a slope of a tangent line at this point, if I drew a tangent line, what would its slope be? Very negative. That's a steep line, and it's coming down as we go from left to right. As a matter of fact, I'm going to exaggerate it. This graph is very narrow. So let's make this picture go from -3 to 3. I'll be able to see just how the difference in steepness happens. Same -10 to 10 on the y, but now our x is only going from -3 to 3. So over here, I've got a fairly steep negative. But as I go to the right, what's happening to that slope? It's getting less steep. And if the slope is getting less steep, then the value is getting less negative. Less negative. Wait a minute. It means I have a negative number and it gets less negative coming up. The graph of my derivative should start down here and come up. Okay, if it's coming up at some point, it should cross the x-axis. It should go from being negative to being positive, because these lines are negative, but these tangent lines have slopes that are positive. So somewhere around here, I should hit 0, going from negative to positive. Then what happens is I continue to the right. If I am just at this spot, the slope of my tangent line has what sign? Positive. But it's a fairly small positive, right? As I get here, what happens? It's a little more positive, but then I see lips moving and hear nothing. Come on, people, talk to me. It looks like it starts to get less positive again, because what happens right about here? I think that's flattened out to 0. And then we start to get more negative. So if I go from positive to negative, I have to hit 0 somewhere in the middle. Why is that sentence true? The intermediate value theorem. It's the reason we did that, isn't it? I had to go from negative to positive. I have to be 0 somewhere in between. I went from positive to negative. I have to be 0 somewhere in between. If I tell the computer, hey, approximate for me at every dot here the derivative, it'll do that. Because under the calculate option above trace is a derivative notation. So I can ask the calculator for the derivative at any spot. Hit number 6, and it'll ask you, what x value do you want to put in? Somebody pick an x value between -3 and 3. 2. I type 2. It tells me the derivative there is -10. But the calculator just did exactly what you wanted it to. Ayana, it said, let's approximate that by moving back and forth and measuring secants and let them get smaller. It did the table really fast because it's a computer, not a slow person like me. So I'm going to say you should do that everywhere. Second, calculate. Option number 6, dy dx is my notation, right? So I type in number 6, and then you'll notice it's got an x value and it's got my little blinker here. That means I can position the spider. Move it to where you want or type in a number at this point. We typed in 2. If I type in 1, it tells me the derivative there. Notice that's not an exact value, is it? Again, it's kind of going back and forth with the table, so there might be some errors due to round off or termination or something like that. I have to take the calculator with a grain of salt. But it's off by 1 part in a million, 10 million. I think that's good enough. Better?
Yeah.
Okay. I wanted to do this everywhere. I'm going to go down to y2. And I'm going to say, I want you to take the derivative of the thing in y1. How did we get our derivative? You just asked me this. What did I do to get the derivative thing? Second, trace to get the calculate menu. Option number 6. right? But when I do that, it goes back out to the graph. That's not where I want to put that, right? That's not where I want to put that. So let me see. If I'm in this menu, there's got to be a way to get the derivative some other place. Under the math button, which is down here on the left, there's an option. See this little arrow here? That means there's more stuff down there. So I go down and down and down and down. Hey, wait a minute. Deriv. The N here stands for numerical, because this is not a symbolic calculator. It just does numerical calculations to think of derivatives. I'm going to use that version. Hit enter. Hey, that looks right. That's take the derivative of something. ddx. Isn't that a notation we came up with on Friday? The derivative of what? I could type the function in again, right? First of all, I need to tell it, you'll notice that little box there is blinking. I need to tell it what variable I'm using. The derivative with respect to x. And now here you can type the formula. Or you could say, go use the thing in Y1. There is a button on your calculator under the arrows that says VARS, V-A-R-S. Stands for variables. Right here. Whole column says Y variables. I want a function. As a matter of fact, I want the function in Y1. Variables, function, the first one. Or you could type the equation in if that's too much of a pain in the ass. Then I have to tell it where to do it. This vertical bar tells me to plug in a number. But I don't want to just do it at one number. I want to do it for every number, right? Which means I want you to do this for every x all the way across the window. I need to put in an x down here. This expression means to the calculator the same thing as this. The calculator is now going to do this job by picking points all the way across and numerically, what's the slope here? What's the slope here? What's the slope here? And it's going to do it over and over and over again. And if you hit graph now, you should see a graph that starts out negative, goes to 0, becomes positive, goes to 0, becomes negative. Hey, wait a minute. I just described this shape, didn't I? Let's see if I'm right. Now, if you've got a color version, you can make these two different colors. I don't have a color version. If I change the graph in Y1, it'll do it again automatically. So it'll start by drawing that graph, and then it will draw the derivative. Here's my first graph, looks like a W. Here's my second graph. Negative slopes, positive slopes, negative slopes, positive slopes. Oh, it gives you parenthesis after the end deriv? Okay, so that's the older version of the software. Okay, so if you don't see that ddx thing, the one that I just put in, so if you see instead of this, if you see this, then what you need to put in is y1 comma x, I believe. Because that says take the derivative of y1 with respect to x at x. I like this. I like this a lot. Did that work? The comma is above 7. It didn't. Okay, hang on a second. This is where I say with a straight face, I don't remember. But I have a Canvas file on our Canvas page about using graphing calculators. Ping. I think our thing about derivatives is in here. No, it isn't. Damn. Okay. In that case, education.ti.com, products, guidebooks for the TI. You have a color one, right? Patrick, you got a color, a CE? Okay. What did I need to do? Oh, yeah, you absolutely have to close that parenthesis. Okay, good. If not, this is where you find the manual. The manual has everything. It may read like it's written in Farsi, but it's there, I promise. Okay, let me go back to 2x minus x to the third, which was our cubic with what looks like a parabola. You'll notice it takes longer to draw the derivative because it's doing those calculations for every one of the points all the way across. Now, in my calculator, there are 96 points from edge to edge on that screen, and this is a 15, 20-year-old calculator, so it's slow. If you've got a more recent calculator, this should be faster. It sure looks to me like this derivative function is a downward opening parabola. I go back to algebra class and I say to myself, parabolas. Parabolas come from quadratic equations, which means if I do this derivative, I should have a quadratic equation. Let's do it. My definition for derivative says to do this algebra and take this limit. So I need to plug x plus h into this equation. Then I need to subtract off the original equation and put all of that over h. A large amount of algebra follows. So multiply all this stuff out here in this first set of parentheses. I need you to take x plus h and cube it out. I need you to take 2x plus h and distribute the 2. Let's do all of that. Now that minus sign is going to change every one of the plus signs when I multiply this out, because this is all positive. I'll get a bunch of cubes and squares and other stuff, but they'll all be added together. That minus sign is going to change them all to minuses. Now, for those of you who are wondering, yes, I really did do that fast because I've done this a whole crap ton of times. But there is also a shortcut for doing x plus h to some power. There's this thing called Pascal's triangle. Anybody heard of Pascal's triangle? Okay, a couple of you, good. If you haven't, I will be glad to go through that after we've finished this problem, but there is a nice, faster way of coming up with all of this. But you could just take x plus h times x plus h times x plus h and distribute the hell out of it. What lovely thing happens in that numerator? Are you sure about that? I've got stuff that doesn't have any h in it. I've got a 2x in the very front there. Oh, right, there's a 2x over here. So this and that cancel. What about this? Wait, there's a minus x cubed minus another minus x cubed. So this and this cancel. And then when I do that, everything that's left on top does have an h. And now, since everything in the top has an h, I can factor that h out. Yes, ma'am.
Oh, it's 2h. I'm sorry. I thought that said 24.
Thank you. Crappy handwriting does fail again. I'll fix it. So I factor that h out. And now the h on the outside cancels with the h on the bottom. The whole reason I did all of this was to resolve the indeterminate form 0 over 0 that I got at the very beginning. So I don't want to deal with 0 over 0. I did the algebra to get rid of it. H goes to 0. What happens? That becomes a 0 because it's multiplied by 0. That becomes a 0 because it's multiplied by 0. The graph of 2 minus 3x squared, a quadratic with a negative leading coefficient, is a parabola that opens downward. Hot damn! I don't know what you're talking about. There is no simpler thing at this point. This is the only way I know how to do these derivatives. Until magic happens. If you believe in magic. I'm not a wizard. My Accio charm sucks, people. I can't transmogrify anything here. Last one I used came from a costume store. This isn't going to cut it. What that means, though, is that many of these problems have algebra that is a nightmare. I believe the example in the text. Yeah, here we go. Page 156. Has this function. I'm just going to set it up. F of x plus h is 1 minus the quantity x plus h over 2 plus the quantity x plus h. So when I go to do my limit, as h goes to 0, this is f prime of x, of f of x plus h minus f of x over h. I get h goes to 0. 1 plus parentheses x plus h minus 1 minus x over 2 plus x all over h. Oh my God. Fractions within fractions and distinct denominators in the upper part of that fraction. Blech. All of the algebra is done for you on page 156. I'm not going to do it. But just in order to set this up, you need a common denominator up here. Then you need to multiply by all the right pieces to get that to be one fraction. Then you have to cancel whatever h will cancel and hope for the best. It does work, though. It does work eventually. I get that. But what is between and covered up by those dots is a large multitude of algebraic sins. That's how the sausage gets made, people. So I can write f prime of x, my notations. Let's see. We had y prime, f prime of x. We had df dx. We had dy dx. We had dxf. We had just d of f. We had a dot. We had all sorts of notations, right? Each of these at a function or at a point. All of these notations in the top row represent a function. In the bottom row, they represent that function evaluated at some number a. That vertical bar there is sometimes called the valuation bar. So we evaluate at a point. And if we know what the variable is, then we don't have to write the x equals. That's why down here it just says at a. But that's at a dot, a specific point. And our graph showed us over a whole section, right? From -3 to 3. You are differentiable in a region if you are differentiable at every single point within that region. Because this derivative is a limit, it is possible that that limit fails to exist. Being differentiable means the derivative exists. So a function is differentiable, means I got a derivative, I did my limit and all worked. But if I do the limit and something's effed up, then I have a problem. An example. Let's think about the function absolute value of x. What's the graph of y equals absolute value of x? which really means this function is defined in two parts, right? This function is defined differently when x is negative versus when x is positive. When I'm negative, the line goes down as we go from left to right. To make a negative number positive, you multiply by -1. So if I put in a negative number, I have to multiply by -1. On the right, my number's already positive, which means I just have to spit back out the number you put in. If I am looking at any point x less than 0, this is a line. What is the slope of this line? Because it's negative. And the slope of this line is +1. So I know the value of the derivative for all the x's less than 0. For all the x's bigger than 0, we have 1. I missed something? What's going on at 0? Let's see if we can prove that. I think it doesn't exist, but I should figure out why it doesn't exist. That would be f prime of 0. The absolute value of a plus h minus the absolute value of a over h, but a is 0. The absolute value of 0 is 0. The absolute value of h is just the absolute value of h. But in order to do this limit, I need to do the limit from the left and the limit from the right separately because the function is defined in two pieces. So I need to do the left limit. Limit as h approaches 0 from the left. Well, when I am on the left, I'm using negative numbers. So that's the limit of minus h over h, because that's the way my function is defined. The h's cancel, and I get -1. The limit on the right, however, what happens on the top of this fraction? What goes here? Just an h, which makes this side 1. Since those are different, this limit doesn't exist overall. I changed direction from negative to positive without going through 0. Wait a minute. You just did a homework problem on this. I broke the intermediate value theorem. What does that mean about the function f prime? It's got a jump in it. Sorry, this way. -1 to 1. It's discontinuous at 0. As a matter of fact, it turns out that if you have a derivative, you automatically get continuity but not the other way around. If my function is differentiable on an interval, then it must be continuous on that interval. So differentiability, having a derivative, is a stronger piece of information. It tells me more about the function than just knowing it's continuous. There are functions that are continuous everywhere, that are differentiable nowhere. They look like they were drawn in the middle of an earthquake. Weierstrass called these monstrously pathological functions. Some of them are amazingly complicated, but they all have the ability to be so jagged as to have no derivatives anywhere. We will save those for later, much later. All right. What things could I see on my graph based on this sentence that would tell me you don't have a derivative? A little bit of a logic exercise for you. Those were things that made me not continuous, right? Differentiable means continuous, so not continuous means not differentiable. Aha. But the absolute value was continuous, and it still failed to have a derivative. So there's more. Hang on. If I have a hole, a gap, a jump, an asymptote, I will fail to be continuous. I will then fail to have a derivative. But I had a continuity. I just didn't have a limit for my derivative, right? And it's this sharp corner that screws me up. Because if I zoom in on that sharp corner, can you tell me what the slope is at the peak there? Well, from the right, it should be negative. From the left, it should be positive. It can't be both. So a corner messes me up. So if I have no way of getting a limit in my limit, I won't have a derivative. So I don't have a derivative at a corner. One other thing. We talked about tangent lines and slopes of tangent lines. What lines do not have a defined slope? Slope of a horizontal line is 0. Give me a line whose slope is undefined. A vertical line. If my tangent line is vertical, then its slope is undefined. Derivative is slope of tangent. So it's one thing to say holes and jumps and gaps, which break continuity, break derivatives, but corners break derivatives. Vertical tangent lines break derivatives. Lots of things break derivatives. We should look at our graphs. Please note, I did the derivative of a function, and I got another function. So what if I took that function and did its derivative? I've done a derivative twice. I have a second derivative. Motion. Change in motion is velocity. Change in velocity is acceleration. That is a second derivative. Change in acceleration is jerk. That is a third derivative. It jerks you around in your car. We can do derivatives as many times as you want, and there are applications to all of them. There better be an easier way or we're going to have a hell of a time. Guess what we do Wednesday? If you came in late, I still have your homework. Come get it from me. That's on attendance today. I will see you all later. Thank you. Thank you.